That process, I think I left it halfway and told you to carry on and complete it and make sure you have obtained some solutions. Now, a few of the students have contacted me and given me their solutions, which mostly are correct. What I have to mention at this point is, ladies and gentlemen, this is a design. So it is in very rare occasions that I expect you to have the exact same solution. In fact, even in the design of the lead compensator, I told you that the technique that I was applying is not only the technique that is available. It is the simplest one that I can illustrate in class. But there are other techniques which include writing code or algorithms that will then allow you to obtain the solution that you need. However, because we are doing this manually, there are several other techniques that one may apply. The technique that we applied in class is one that involves drawing geometrically, coming up with a diagram as illustrated on your screen. And in some of the drawings, we made estimations. That is, we estimated certain angles. We sort of fixed certain angles so that we are able to carry out a calculation for both the pole location and the zero location. Now, the idea here is so that we arrive at a solution that is workable. It is not going to be the exact same solution, because this is a design, and design problems usually have different solutions. But as long as at least the solution provides is the solution, first of all, is able to relate with the problem, the solution is believable. Okay. Now, I because of the geometric drawings that I did, I carried out my solution or my design and obtained the pole location and the zero location. Now, you may arrive at your solution, because for me, this is based on my design. That was the compensator that I came up with. Now, you will notice that you might have used a different technique, but your solution will not be far away from the answer that I have here. So in essence, I don't expect all of you to obtain the exact same solution. But if you use, for example, if you use my method, then you will more or less arrive at the same solution. But I will expect variance. The values will deviate, but not by a lot, just by some margin, which is acceptable in design, because in design, no two solutions will be exactly the same. A few things can change here and there. So I hope that that is very, very, very clear, that because this is a design, you don't expect to restrict yourself to the exact same solution as the next person. Sometimes you will see, especially when we do the lag compensation, that you're supposed to come up with a trial and error figure. So, somebody can select 2 as their figure. Somebody can decide to select 3. Somebody can decide to select 2.5. So both will lead you to some solution, or all of the choices will lead you to some solution, but they can never be exactly the same. Okay. Now, again, I encourage you that in obtaining the compensator, like now, this was my lead compensation, could you please also go ahead and obtain the subsequent gain? Use the magnitude condition to obtain the gain. It's very important. Now, I obtained my gain as 0.54. I expect that you have a similar solution, not exactly the same, but something similar that is acceptable. After all, like I've said, it is only a design. It is only a design. So far, ladies and gentlemen, we have talked about the the lead compensator, and we have agreed that the lead compensator, especially for those who have been keen, has only 2 main goals or objectives. The lead compensator is used to improve the transient response. It is used to improve the transient response. Okay, the settling time and all that stuff. It is also used to improve on stability. It is also used to improve stability. These are the 2 main objectives of a lead compensator. So you will always see that in a lot of design, especially in control systems that involve feedback control systems, we use a lead compensator first because we intend to achieve one, the transient response need to be the right response that we expect, and also we need to improve the stability of the system. Okay. However, that is not all in tuning a system. When we want to tune a system, there are other things, and that is where the lag compensation come in. So the lag compensator, its main objective is just one, and its work is to reduce the steady state error. Reduce the steady state error. This is the main purpose of using a lag compensator. In fact, you will always see that in any question involving a lag compensator, you will be asked for the expected, or you will be told the expected steady state error so that you reduce it. It is all about reducing the steady state error. Unlike the lead compensator, where you will be told that, okay, in our design, the expectation is such that we need to achieve stability, but at the same time, we need, the natural frequency or the damping frequency to be of a certain value. In lag compensation, we just need to reduce the steady state error. Once we do that, we are done with that design. And of course, now the lead lag compensator, like I've said, is left for you, the lead lag compensator. This is left for you, and of course, it takes into account all, let me just say, the above issues. All the above issues. So here is where you really want to not only improve the transient response, you want to improve on the stability, and you also want to reduce the steady state error. So it combines both, okay? So that I'll leave for you. The other thing that I expect that we remember is that for the compensator, for the lead compensator, we had this transfer function we were expecting. Let me just use a different case so let me just say S plus Z1, S plus P1. So that is the design for the lead compensator. For the lag compensator, as we shall see today, follows the same type of design where you also just need to come up with the pole location and the zero location. But here, the rules for finding the pole location and the zero location are slightly different. Let me use let me just use a different illustration. This is just for illustration purposes, so let me use Z2 and P2, okay? And of course, what I expect you to do is now when you do the lag compensation, where you now have to combine both the lead, okay, and the lag. I'll write it like this, where you have to combine the lead and the lag compensation. So I didn't even write it properly, and let me just indicate that it should be S and then lag by S. So it's simply having to cascade both the lead compensator and the lag compensator together and to join the plant system, and then you have your solution. Okay, so that is left to you. Now, in the next 40 minutes or so, allow me to introduce you to the lag compensator in depth and just tell you what is expected. And then from there, I expect that you can actually now attempt solutions. So at the end of this study, I'm going to try and solve one problem. And then hopefully from there, you have to carry on your own. So how do we design a lag compensator? So let me just say how to design a lag compensator. This technique is totally different from the way we design a lead compensator. So you should pay proper attention. So how do we design a lag compensator? We have agreed that a lag compensator is going to be represented by a transfer function for the lag compensator itself. So we can just call it S plus Z over S plus P, okay? Because we are not differentiating it from any other anyway. So here, like I've told you, the objective of the lag compensator is just one. We need to reduce the steady state error. So in most times when you're given an open loop transfer function, you need to determine the steady state error of that open loop transfer function. Then you will see then what is the value that is required, the expected steady state error. So there's what we call the steady state error. The steady state error will be denoted by that, okay? And this usually refers to the steady state error for the uncompensated system, the system that has not been compensated. That is just the plant system, just the plant system without compensation. That is what we refer to. But then there is the compensated steady state error, okay? So the compensated steady state error is what we need to come up with, compensated steady state error. So this would be denoted by ESSC. So this is now the compensation. Okay, so you'll find that your plant system has a steady state error maybe of 0.5, but we want you to reduce the steady state error to 0.2. Okay, that's just an example. Okay, so then the technique that I'm going to teach you today is one that is just used to help you figure out the right zero location and the right pole location so that you can reduce the steady state error from an example of 0.5 to 0.2. Once you have those, then you are home and dry. But you have to be very careful on certain principles, okay? So let me just say guidelines. Guidelines. Remember, in our design, still we have to do, all we have to do is find the position of the zero and the position of the pole. So guidelines to choose the zero and the pole. The guidelines to choose the zero and the pole. Can I please just get an indication that you can hear me?
Yes, we can.
Yes, you can.
Thank you very much. Thank you, guys. It's because my internet is intermittent, so I have to check with you. Now, here, we just need to know how then can we determine the zero location and the pole location for the lag compensator. The objective is to reduce the steady state error, okay? Now, the first thing that we must always understand, especially in the choice of the zero and the pole, is that the zero and the pole of a lag compensator must always be as close as possible. Let me just indicate it. The zero and the pole, and this only happens for the lag compensator. The zero and the pole for the lag compensator must be as close as possible. And I'll explain to you why. So, in essence, what we are saying is that if I take the transfer function of the lag compensator, it must be approximately, let me use the right terminology, not equal to, but approximately equal to 1. That means this value here is approximately equal to 1. The zero, and that just goes to show you that the zero position and the pole location are almost at the same point. That's why if you find the transfer function, you almost get 1. And the reason is very simple. Remember, when we were designing the transfer, when we were tuning our system using the lead compensator, the idea was when we were trying to determine the zero and the pole location, when we were using the lead compensator, the idea was to use the angle condition, and so that all the angles and the pole, all the angles of the poles and the zeros must be equal to 180 degrees or an odd multiple of 180 degrees. Okay? What I mean is, if you remember in the previous case, we had to determine and say, okay, if this is the, that was the desired location and we had certain poles or certain zeros, we had to draw angles to this desired location, okay? And we had to say that if we were to add our own pole and our own zero, again, we need to check, but we make sure that all these angles were to add up to 180 degrees. So in this case where we are using the lag compensation, we have to ensure that the pole and the zero location are as close as possible. What that means is, remember, again, this is just to remind you, ladies and gentlemen, we had said previously that in a lag compensator, we need to have the pole closer to the origin and then the zero. Okay? And the lead compensator was the opposite. Here, it is the pole that's closer to the origin and then followed by the zero. Okay? We are saying that, let's say the desired location, the desired pole location is there. If we draw an angle here, we are saying that the angle separating the pole and the zero here should be almost 0 degrees. Why? Because at the end of the day, we want to see that the total angle should still add up to 180 degrees. But remember, when we were using the the lead compensator, the angles were made to add up to 180 degrees. So if we are adding the lag compensator, we don't want to add any other angle. We want to add 0 degrees. So the only way to add 0 degrees to the entire combination is to ensure that the zero and the pole location are as close together as possible. Very, very, very close. And that is why the transfer function that we are supposed to come up with should almost be equal to 1. Of course, it is not going to be equal to 1, but it's approximately 1. Okay? Because as long as there's a position for a pole and then there's another position for a zero, okay? And we've made them as close as possible, there's going to be a pole location and a zero location. But we want them to be very, very, very close together. I'll give you the guidelines of doing that. Okay? So please just remember that because we had already designed our system or tuned our system using the lead compensator, we had used up the angle or the angle condition was already applied. So in this case, we don't want to introduce another angle. Remember, the idea is not only do you want to improve the transient response of your system and also improve the stability, you want to reduce the steady state error. So now it means that if we add up another angle for a pole location and another angle for a zero location using the lag compensator, it's going to affect the transient response. So making the pole and the zero for the lag compensator, if they're wide, if they're far apart, it's going to significantly affect the transient response. But now we don't want to change the transient response. We don't want to improve the stability of the system. We just want to reduce the steady state error. So the only way to do that is to use a pole and a zero that are as close together as possible, because if we do that, then it's going to ensure that we don't affect the transient response of the system. We only reduce the steady state error. Okay, so to illustrate it properly, before I continue, is, let me say, without compensation, let's just say there's a system here. Let me draw a system without compensation. So if, for example, we had one system here without compensation, and the compensation I'm talking about here is the lag compensation, okay? And then with compensation, if we have another one here with compensation. My point is, if, for example, and this is just a typical illustration, I'm not saying this is just for an arbitrary value. So let's say there's a system with 3 poles, okay? So this is a system that has not been compensated at all. And let's say that our desired pole location is, so that's our test point, okay? That's the test point. So, of course, remember, if we draw an angle, if we get the angles, we are going to have theta 1 theta 2, and theta 3. So this system is not compensated. But if we add our compensation, it means therefore that now we are adding our 0 and our pole that is responsible for the compensation. So if we add our compensator, we are still going to have our 3 poles there. We are still going to have our desired test point there. And we are still going to have our theta 1, our theta 2, our theta 3. But ladies and gentlemen, we are doing a lag compensation. So our compensation needs to add the pole and the 0. I've told you they must be as close as possible, not just from each other, but also to the origin. So that's also very important. For us to achieve a proper lag compensator that will help reduce the steady state error, the distance or the gap between the pole and the 0, this pole here and this 0, must be as small as possible. But also, both the pole and the 0 should be as close to the origin as possible. Okay, so now we'll be adding these 2 angles here for the pole and the 0. Okay, so let's just say theta P and theta Z. Okay, now here we always say that theta 1, if it's a pole, it's you subtract, minus theta 2 minus theta 3 should be equal to 180 degrees. If we compensate, we are still going to have minus theta 1, because it's a pole, minus theta 2 is a pole, minus theta 3 is a pole. So minus theta P, because it's a pole, plus theta Z, which is now a 0, because for zeros we add, I hope you haven't forgotten that, should be approximately equal to 180 degrees. So notice, this is already contributing 180 degrees, and it is already here. So therefore, it means that these two here should contribute almost 0 degrees. That's exactly why I was explaining that the only way we can make sure that the pole and the zeros cancel out, that's basically what we are saying, that the pole and the 0 cancel out, they must be as close as possible. And they must also be closer to the origin as possible. That is a very, very important point in the design of the lag compensator. So please remember that point. So actually, I can actually write it here for the number 2, that the pole of a lag compensator, the pole of a lag compensator should be close to the origin. Okay, remember, that's why the pole is the one that is closest to the origin, but it should be as close to the origin as possible. In addition, and this is only for a design perspective. This is only a design perspective. In addition, the ratio between the pole and the 0 should be very large. In fact, the idea is we usually say approximately no, let me leave it there, and then I write a third one because I don't want to make it so wordy. So the idea is the ratio between the 0 and the pole, this Z over P, should be large. Actually, it should be it should lead you to a large, let me just say KV, the ramp constant. I told you how to calculate the ramp constant. So the idea is to make sure that, one, the pole that you're designing is as close to the origin as possible, but also the ratio between the 0 and P should be very large. The last one, this one is the key, another key design element. Again, remember, just a design. Somebody can use a different avenue for this, but still obtain similar solutions. And so what I wanted to say is this is the last design element before we do an example. So I want to put it such that the pole location, you can see the pole we've said should be as close to the origin as possible. Now, you would want to ask, what then should be the 0 location from the nearest pole, or what we call the dominant pole? Okay, so the 0 location should be at least 50 times apart from the dominant poles. From the dominant poles. Okay, I'll show you what that means. So the 0 location should be at least 50 times apart from the dominant poles, meaning the distance here, the distance from this 0 location and the dominant pole should be at least 50 times. So that gap should be at least 50. It doesn't have to be 50, but at least 50. So in somebody's design, they can pick 60, you can pick 70, you can even pick 100. It's fine. But it should be at least 50 for you to achieve the right transfer function that we are looking for. The idea here, again, ladies and gentlemen, is to ensure that the transfer function for our lag compensator is approximately equal to 1. The reason why we want it to be approximately equal to 1 is because we don't intend to change the transient response of the system. We also don't intend to change the stability of the system. That has been taken care of by the lead compensator. Here, we only want to reduce the steady state error. So we don't want to affect the angle condition. We don't want to affect the magnitude condition. Those conditions are already fixed by the lead compensator. Here, we only want to reduce the steady state error. So our design should be such that the pole and the 0 that we are picking should be as close to the origin as possible and should be at least 50 times away from the dominant poles of your root locus. Now, again, if I do an example, that point will sink home. Okay, so I'm going to do an example in a minute. The other thing that I need to, before I do the example, that I just need to illustrate for those who probably have forgotten, but I expected you to know by now, is that to obtain, so if, let's say, this is just a set of points that I need to do. When given, how do I call that? When given an open loop transfer function, I don't have time to write all that stuff. So when given an open loop transfer function, okay, G of S, okay, first, the steady state error, I'm thinking faster than I'm writing. The steady state error should be given by this term. This you have to know. Nobody will tell you this, but if you've done control systems before, that is what gives you the steady state error. Okay, what I mean is, for example, let me just say, for example, if you say something like 5 over s squared plus 10s plus 3, you know, if this is GS, if this is GS, okay, if that is your GS, then you can say that the steady state error would be given by the denominator. So you take the denominator and substitute S for 0, okay? So S is 0, but only the denominator term. That would be GD of 0. So it would be 0 squared plus 10, 0 plus 3 over GD of 0 again is 0 squared plus 10 0 plus 3 added to the numerator with s equals to 0. The numerator of our term is just 5 because there's no s. So you solve for this. So this is 0, this is 0. The numerator there is 3 over the denominator is 0, this is 0, the denominator is 8. So here your steady state error is 8, which is about 0 point into 30. I think it goes 3 times, which is 24. Okay, into 60, it goes 6 times or something like that. Okay, so that becomes your steady state error. So please know this is a very, very critical formula for obtaining the steady state error. However, we also have other formulas that I'm going to show you. In fact, the best way to show you is now let us do a design. So what I want to do here is to do this design using the exact same problem we were solving previously. So the question was, because it's a continuation of what we were doing, we had this example here, and we designed it using a lead compensator. Remember, when we design using a lead compensator, we are trying to improve on the transient response and also improve on the stability. But now we want to design a lag compensator so that we improve or reduce the steady state error. That's the word. We want to reduce the steady state error. So the system remains the same. So let me rephrase it properly. So let me rephrase properly. Let me just see what the transfer function is, because I don't want to come back. The transfer function is 145, 10, 145. Okay. 10, 145 is the transfer function. So let's do an example. Remember, we are designing this problem using a lag compensator. So question, typical, again, this was in your exams, I think 2 years ago. It says, design a lag compensator. It says design a lag compensation. Design a lag compensation for the system G of S equals to 10, 1, 4, 5 to reduce the steady state error, to to 0.1. Okay, that's very critical. So notice here you're only given one parameter that is expected, because it is assumed that here when you're designing the lead compensator, that will take care of the transient response and take care of the stability. But when you're designing using a lag compensator, all you're taking care of is to reduce the steady state error. So how do we solve this? Now, just again, very, very simple. This is a very, very simple design. You can do it, but you just have to be very keen. Okay. So first of all, we have been asked to reduce the steady state error. You should ask yourself, what is the steady state error of our system before it's even, because this is what is expected of us. Meaning, if we check the steady state error of this system, it should be higher than 0.1, because the essence of the steady state error is to reduce, the essence of a lag compensator is to reduce the steady state error. So it means that we are expected to have a steady state error of 0.1, meaning currently our system does not exhibit a 0.1 steady state error. It must be a value that is higher. Let us confirm that. So the uncompensated steady state error, I told you, is just denoted by that, should be given by, again, this formula, I told you to remember it, over GD of 0 plus Gn of 0. N stands for numerator, D stands for denominator. I think that should be very clear to you right now. So let's do that. Let's start with filling up the denominator. So you take the denominator of your G of S and substitute S for 0. So we'll be having 0 squared plus 4 0 plus 5, divide by, again, the same thing, squared plus 40 plus 5, plus the numerator, and we make s equals to 0. The numerator is just 10, so we just put 10 there. Okay, so when we solve this, this is 0, this is 0, this comes to, this is 0, yeah, this is 5, divided by 0, 0, 15. Okay, so therefore you can see that here our steady state error is a third, okay, 0.33. So you can actually see that it confirms that the steady state error of our system is actually higher than what is expected. So we are now expected to reduce this steady state error of your plant system to 0.1, which is now the compensated system. So to reduce it, first of all, remember the conditions here. These three conditions. The 0 and the pole for the lag compensator must be as close as possible. The 0 location and the pole location must be as close as possible so that the transfer function is approximately equal to 1. Number 2, the pole has to be as close to the origin as possible. And number 3, the 0 location should be at least 50 times apart from the dominant pole. Now, let's go back and use those guidelines. Here, first of all, for you to obtain the relationship between the 0 and the pole, meaning what is the ratio between the 0 and the pole, the 0 and the pole. Now, for lag compensation, we have a formula for obtaining the relationship between the 0 and the pole, or the ratio between the 0 and the pole. And for a lag compensator, that ratio, and this only applies to the lag compensator. Please do not use this formula when you're using lead compensator. So for the lag compensator, to get the relationship between the 0 and the pole, this is just the ratio. It's not telling us the location of the 0, neither is it telling us the location of the pole. It's just telling us the ratio of the 0 to the pole location should be given by GD of 0 minus the compensated steady state error of GD of 0 divided by the compensated steady state error GN of 0. So this formula only tells you the ratio between the 0 and the pole. It is what determines what we had talked about here, that in addition, the ratio between the pole and the 0 should be very large. That when we say large, that becomes relative. So to know it, we have to use this formula. What is the relationship between the 0 and the pole location in terms of ratio? Okay, so it's given by this formula. So in our case, again, it's very easy for us to determine that ratio. Then from there, we'll move on to finding the exact locations. Okay, so we now start, because remember, in our case here, the 0.1 here that we have in our design, this is the compensated. This is our compensated, because it's the one that is required after compensation. The actual one is 0.33, but after compensation, we expect it to be 0.1. So the 0.1 is the compensated steady state error. That is what is expected. So let's use that information to get this relationship, or the ratio between the 0 and the pole. Again, take the denominator of the term, put it to 0. I think we already did that, and it gave us 0 squared plus 4 plus 5. So that was giving us 5 minus the compensated value is expected to be 0.1. Okay. This is 5. Remember, I showed you how to find GD of 0 and GN of 0. You simply take the numerator or the denominator and equate S to 0. Okay. So divide by the compensated value is expected to be 0.1, and GN of 0, we found it to be, when we took the numerator, it was 10. The numerator was 10. Okay, so if you solve this, I think you get this is 5 minus 0.5. That should be 4.5 This is 1. So the value here should be 4.5. That is the ratio. So that means the gap between the 0 and the pole location, or the ratio between the pole and the 0, the ratio between the 0 location and the pole location should be 4.5. Okay? Now, these ones have formulas for determining them. How do we determine the condition that was given here? That we need to know, look at number 3, the 0 location. Remember in our design, I think I drew, in our design for a pole for the lag compensator, the design is such that, I think I already indicated that, it is the pole that is closer to the origin, and then the 0 follows. Okay? So we want to know where is the dominant pole for our system. I'll show you that in a short while. But for those who are writing down, you can indicate at this point so that it's easy to explain that we shall obtain a compensated steady state error of 0.1 if the 0 to pole ratio, if the 0 to pole ratio is 4.5. That's the significance of obtaining that 0 to pole ratio, because it tells us what ratio of the 0 to pole location will give us a steady state error of 0.1. So that is the significance of that. Now, our system, we had done it previously. This system, we had done it previously. And you saw that when we drew, I think we did it previously, when we drew the 0 and the pole location. Let me just check it. Sorry for the scrolling that appears on your screen. I'm trying to find the dominant poles. You can see from our diagram when we drew it, the dominant poles, you remember, these are the dominant poles. One was at -2 plus J 2.4. No, -2 plus J1 and -2 minus J1. Those are the dominant poles. Okay, so our poles are really at -2. Sorry again for the scrolling, I had to do that. So it means our poles originally were at this point when plotted, where this was -2. Okay, they're at point -2. That's the imaginary part. We are not interested in our design on the imaginary parts, because you know that our pole and 0 location are always put on the real axis. They are never put on the imaginary axis. For our design, for the lag compensator and the lead compensator, we put our pole and zeros on the real axis. So it's like saying, now, what did I tell you in rule number 3? So if our pole, the dominant poles are at -2, that is on the real axis. Forget about the imaginary. But on the real axis, they're at -2. So what should be the distance to the 0? Because the pole will also just be close by there. So what is this distance here? Because that's what will give us the location of the 0. So we say the location of the location of the dominant pole, you can actually just say the location of, remember, the dominant pole is always a pair. It's always a pair of poles. So the location of the dominant pole is -2 in this case. So therefore, the location of the 0 should be equal to, remember the rule that I indicated here, that the 0 location should be at least 50 times apart from the dominant pole, at least. So therefore, if the dominant poles are at -2, then the 0 location should be at least 50 times. So if the dominant pole is at -2, so I divide that by 50 to give me the zero location. And this is going to be minus 0 point, I think 0.04. So that should be the location of the zero. I'm using a very arbitrary value of 50. You can put 60, you can put 70, you can put 100. This is simply design. Okay? So therefore, if that is the location of the zero, the location of the pole should be, remember, the ratio of the zero to the pole should be 4.5. So the location of the pole should be, the zero location is at minus 0.04, and I have to divide by 4.5 for me to know the location of the pole, so that the ratio is 4.5. So if you divide this, you get minus 0. Let me just punch this in and find the solution. 4 divided by 4.5. Yeah, so you get 0. I think 0.0089, something like that. Okay. So now this becomes the location of your pole. So notice that the way we determine the pole and the zero location for the lag compensator is totally different from when we are using the lead compensator. Here, we have made certain assumptions. One, we have decided to use the zero to pole ratio formula so that we know how far should be the zero to the pole. Okay. Then number two, we have also decided to use the rule that the zero location should be at least 50 times apart from the dominant poles, or the pair of dominant poles in this case. So that is what gave us the minus 0.04. So if we use the ratio, then we obtain that. So therefore, our C, we're calling it lag. This is a lag compensator. Should be given by S plus 0.04 over S plus 0.0089. Okay, that is our design for the lag compensator. The idea is simply to come up with the zero and the pole location that would reduce the steady state error to 0.1, the compensated steady state error, because our system exhibited a steady state error of 0.33. So to reduce that, we needed to have a zero to pole location of 4.5. Then I've shown you how to determine the zero location. You just make it at least 50. So somebody would have decided to put this as 60. Still, your design should be correct. In essence, what we are trying to do is, because we don't know what, you can try and divide 0.04 divided by 0.0089. You will see that the value is tending towards 1. The value, this is approximately 1. Okay. Yeah, that should be. It will not be exactly 1. So we are using the approximate sum, but it should be 0.9 something, which is approximately 1. So that is the essence. So even if I chose this to be 60 or 100, if you chose the 50, you made it 100, and then you use the same formula, the pole, the zero to pole ratio, to obtain your own value for the pole location. If you divide those, you still get 0.9 something. That's something that is approximately equal to 1. That is the design. Remember, the lag compensator only seeks to reduce the steady state error. It doesn't want to change the transient response, meaning it doesn't want to play around with the angles. It also does not want to play around with the magnitude condition, because it's going to affect stability, and already stability is determined by the lead compensator. The lag compensator is only to reduce the steady state error, and that is it. So ladies and gentlemen, that is how you obtain the design using a lag compensator. I hope that is very clear. So let me give you work, because I am done in the next few minutes. So this is exercise. I want to see if we are able to solve this problem on our own. So I want to use, and I hope you're going to remember, this is only to test the lag compensation. So the exercise here is, I hope you're writing it down, design a lag compensator for the system G of S equals to 5S plus 1 divided by S squared plus 13S plus 16. So design a lag compensator for that system to reduce, to reduce the steady state error to 0.05, to reduce the steady state error to 0.05. Very important. Please remember the rules. Please remember the formulas. So you'll need to know, actually, let me see what the steady state, the uncompensated steady state error. We said that was GD of 0. I shouldn't do this. I'm only just trying to see what the steady state error is. GD of 0, so that I make sure that 0.05 is a reliable information over GD of 0 plus GN of 0. So GD of 0 is going to be 16, okay, over 16 plus GN of 0, okay, should be 1. So that's going to be 16 over 17. So please change this, just change this value. Change this 0.05, that's too low. Let's make it 0.2. Let's make it 0.2. Please change that to 0.2. So the steady state error I've already confirmed here is going to be 16 over 17, which is 0.9 something. So let's change it to 0.2. Good. So I expect a solution on this. Again, you're not restricted to picking this value as 50. As long as it's a value between 50 and 100, I don't have a problem. Ultimately, the solution of your design should be such that the lag compensator has a transfer function that is approximately equal to 1. So is there any question, ladies and gentlemen? Because this is where I end my discussion with you on the compensation. In next class, we are starting a new topic, and that is the, I think the next class we are supposed to do a new topic. This is 5th year. So our next class, I am going to introduce, I'm not going to discuss root locus anymore. The rest of the stuff, I'm going to start state space representation. State space representation. Another technique of representing control systems is using matrices or matrix. So that's state space representation. So that will be our discussion in the next class. If there is no question, I think I want to end the class here.
I have a question.
Yes, please go ahead.
I was asking if our system has more than 2 poles, how do we determine the dominant pole?
Okay, that's a good question. I thought you would go and try and figure that out by yourself, but okay. In any control system, it is always assumed that there is a dominant pair of poles that really are responsible for the structure or the shape of the root locus. Because whenever you put in the poles, you will notice that there's a a set of poles that are usually the ones that play a key role in the shape of the root locus, such that if you remove that pole from that location, then the shape of the root locus changes entirely. So they are called dominant because they are the ones that are responsible for the shape of that root locus. So if the root, if the pole is removed from that location, then the shape of the root locus changes entirely. Let me just give you an example, okay? Let me just give you an example. Sorry, I stopped sharing. Maybe I did that too soon. But let me give you an example. If I plot a root locus like this, I think we've plotted this several times. Some of these just keep ringing in my mind. So now, if you look at this sort of setup, we know, of course, that the root locus exists here. And there's another root locus here. Now we don't need to tell you more about that. But clearly you can see that because of the proximity of this pole to this zero, that is where it will terminate. So that leaves us with these two poles that must terminate at zeros which are at infinity. Now, notice that it is these two poles that are going to determine the movement or to the zeros at infinity. So I don't know whether we are going to go left or we're going to go right, but the idea is the shape of the root locus will be determined by the trajectory of these two poles. So in any transfer function, in any control system, when you look at the transfer function or the open loop transfer function of any control system, the assumption is there is always a pair of dominant poles that really are the ones that are responsible for the shape of the root locus. Their trajectory is what is key. Remember, these two are, their trajectory is almost predictable, and it's insignificant because it's just lying on the real axis, such that you remember, if I removed one of this pole and maybe took it this side, then the entire shape of the root locus is going to change. So this becomes like our dominant set of poles, okay? So this is a dominant pole, this is also a dominant pole, okay? But since we are doing our design and we are putting our poles as close to the origin as possible, so this is the value we are going to take, the one that's closest to the pole, because you want to take you want to make your zero at least 50 times. The zero location should be 50 times away from the closest dominant pole, okay? So the dominant poles are always just determined by, and usually you will find that there are pairs. So if you solve, if you what's the word? If you factor or you get the roots of G of S and you find a complex pole, usually those complex poles are typically the dominant poles, because they're the ones who are going to determine really the shape of the root locus. Their trajectory is what is important in the root locus. But even if they're not complex in nature, like in this case where they are all just on the real axis, you can still see that it is these two that are dominant, in the sense that it is them that play a big role in how the shape of the root locus looks like. So I hope that is clear for you.
Yes.
Iko sawa? All right.
Yes.
Kuna swali nyingine, guys? Because I'm no longer going to discuss root locus with you. I'll go straight to state space representation, which is a totally different thing. So this is where we end our root locus. Please do that work and do as many examples as you can, and then just practice how to plot root locus, sketch root locus, determine the critical points, and also how to design using root locus. So because of time, we'll move on to state space representation, because I quickly need to do the state space before we move on to another third topic, which is very also equally important. We'll use the state space again also to make our own design. So it's not just state space representation, but also how do we design control systems using state space representation. So thank you very much. Time is up. Wish you well and see you next week. Goodbye.